Last page, we're almost there. Two more examples. The first example, we have a definite integral here from 0 to 1, and we're looking at x minus 1 over x plus 1. So since we're dealing with natural log integration and kind of a 1 over u du pattern is frequently what we're looking for, I'm going to say let's go with this just for a moment and let u equal x plus 1. So let u equal that denominator. So I'm kind of moving toward this 1 over u du kind of thing. When I take the differential of u, I get dx. Right? And so that essentially looks like this. Try to kind of keep your attention focused on this for just a moment. Excuse me there. All right. So that gives me the something over u du. All right. But again, I need an x minus 1. I need basically the u equivalent of x minus 1 there. And I don't have that from my du or my u. So again, this is one of those sort of tricky examples where I want to focus on how I can get x minus 1 as a function of u. So if I solve this for x, I get x equals u minus 1. So if I need an x minus 1, that's going to be equal to u minus 2. So then I make that substitution. Take a second here and notice think about if you notice anything else that's changed in that integral. Maybe you notice that our lower and upper limits used to be 0 and 1. Now they are 1 and 2. So I've changed them from x equals 0 and x equals 1 to u equals 1, u equals 2. So I'm going to challenge you to think about that and where that came from, and bring any questions you have to class with you. All right, so moving on in this problem, now we have this u minus 2 over u. We don't have anything that just fits that pattern nicely, right? But you notice that the denominator has one part, or one term. The numerator has two terms. I'm going to split this up into u over u minus 2 over u. And the reason I can do that, well, the reason I want to do that is because now I have a nice simple, I have integral from 2 to 1 of 1 du minus the integral from 1 to 2 with a coefficient of 2. This just becomes 1 over u du. So that's a nice one. All right. I have the antiderivative of 1 is just u, or the antiderivative of 1 du is u. Antiderivative of this is 2 times natural log of the absolute value of u, and I'm going to evaluate these from 1 to 2. All right, so again, I plug in the 2, minus, I plug in the 1, and then that will simplify down to this. And again, I'm going to challenge you to think for a few minutes about how I went from this step to this step. There's definitely some work hidden in there. I want you to think about that a little bit and bring questions you might have to class with you. It's definitely something we can talk about in class, but I at least want to challenge you to think about it a little bit on your own first. All right, so the last example we're going to work on, I'm just going to cover this up for a second here. Looks like this. All right. So as I get examples like this, this is I think a great example for us to really think about. I have 2x cubed plus x over x squared plus 1. Now, as I'm thinking about natural log integration, I'm automatically my brain is in this pattern where I'm thinking, okay, I want a 1 over u du. Okay, if I am in that pattern, it might be reasonable to say, well, I'm going to let u equal that denominator. Right? But the problem becomes when I take the differential of u, the power of u always gets reduced 1 when I take the differential. Right? So I have now du equals 2x, and I need this 2x cubed plus x. So this kind of u substitution isn't really going to get me anywhere particularly helpful. What I want you to notice about this problem, and look for problems like this in the future as well, is that the power of x is higher in the numerator than in the denominator. All right, and I don't know if I want to say every time, but very frequently, the approach we're going to have there is to divide this out. So we end up with this, but it's worth taking a few minutes to talk about how I got that. I'm basically going to do 2x cubed plus x divided by x squared plus 1. Okay, so I have that kind of set up over here on the side. So I have 2x cubed plus, I'd like to have a placeholder for that power of x that's missing. So I have 2x cubed plus 0x squared plus x divided by x squared plus 1. So I'm going to do polynomial long division here. So I look at these leading terms. 2x cubed divided by x squared is going to give me a 2x. And I like to line them up over the corresponding powers of x in the original numerator. And now multiply this 2x down here. So 2x times x squared, the leading terms should always cancel out. That's where I got that 2x from in the first place. 2x times 1 is, well, it's 2x. Now I subtract 2x cubed minus 2x cubed is 0. 0 minus 0 is 0x squared. X minus 2x is negative x. Now when I go to divide, I notice that this power of x is less than this one. So I really am done, and this is just my remainder. And therefore that's where this 2x, that's where that is. 2x minus x over x squared plus 1. So the remainder is written as a fraction, and I have this kind of form now. Now this is a very easy antiderivative to take. It's just x squared. Right? And this part now is what we're going to focus on using u substitution, and really actually this is a fairly easy u substitution problem as well. So we're going to let u equal that denominator now, x squared plus 1. And now we do get 2x dx. I forgot that up here. Should have had a 2x dx up there. So I got a 2x dx here. That accounts for my x dx. Let's see, but I actually need a 1/2 as a coefficient there. That's not very legible. I tried to squeeze it in there. That should be a 1/2 here. And I put that in there. Yeah, I guess I don't really need it till here after all. So I did put the 1/2 in there. When I go into the u realm, I need a 1/2 to offset this 2. So now I have a nice neat 1 over u du integral. I can integrate that this way and then plug my u back in, and I still have my plus c since it's an indefinite integral. Alright, so those last two are pretty good examples of more complicated types of u substitution which involve natural logarithms in some form.